So how do we do the ANOVA? What are the steps?
When do we use the one-way ANOVA? It's very simple. We have one independent variable with more than two levels. All right, so I'm going to reorder our steps and readjust them. I'm trying to make less work for you. So number one, yes, 0. We still do our outlier examination. We state our null and we draw our null picture. We're still doing that. It's just different based on the different tests. We run our SPSS, PSP, R output, anything that we need, we do that second. We get our t-test, our p-value decision, and we interpret the test statistic. 4, we calculate our effect sizes. 5, we get a graph. 6, we get a short interpretation that I'm really cutting back on, and you'll see that when it comes up. When we have outliers, we still have to examine them. So we just plug in the numbers in each of the experimental conditions into the MAD outlier detector. So for this example, we take all the scores in the control condition, throw those in MAD. We see if there's any outliers. We take all of the scores in our 10-gram condition, throw those in MAD. We take all of our scores in our 100-gram condition, throw those in MAD. Now, if it's between subjects, we have different participants in different groups, and we find an outlier, we just remove that one piece of data. But if we find an outlier, and we're doing a within subjects test, we have to remove all their data. What is our null? Our null is that all the population means that we are sampling are the same. So essentially it's mu1 equals mu2 equals mu3 equals mu4 equals mu5 equals mu6 if you have more than three means. Or you can state this in a much easier way. Our F ratio is 1. That's the F ratio where there is no effect. State it the last way. Now, if you need a refresher about why the F ratio is 1, that's because the F ratio is signal plus noise over noise. And when we have no signal, noise over noise is always equal to 1. That's why. And then you're going to draw your null hypothesis. It's not a symmetrical graph anymore. It's an F distribution where the F distribution starts at 0 and ends at positive infinity. All right, so you put those on your graph. We are trying to figure out our F calculated or our F sampled, right? That's not a minus, that's just a label. So we're trying to figure out, okay, from our F calculated, what's our p-value? That's all we're trying to do here. The distribution goes from 0 to positive infinity. It's one-tailed. That's our p-value. There's one other thing I got to talk about in terms of this distribution. So the degrees of freedom that we have affect the shape of our distribution. That's all I'm really going to say. This isn't that different than T, but essentially we still have to remember that standard F distribution that I showed you a slide ago. So you'll see based on the previous information, everything's the same here, except you have to put your degrees of freedom, both of them, on this graph because that's saying we have different F distributions. So our second step is just use our computers to get all the data we can. All right, step number 3, calculate your test statistic F. And remember that our F ratio is important. F minus 1 tells us our signal to noise ratio. I've talked about this before. I would like a signal to noise ratio interpretation. So F minus 1 is the signal to noise ratio. And our p-value, did we disprove the null? Do we know nothing? Essentially, those are the two things we have to say, our signal to noise ratio and our p-value. Now, the proper effect size for an F test is called partial eta squared. It has 3 different symbols. You can see it there. All it is the sum squares of the effect divided by the sum squares of the effect plus our sum squares error. Let's examine this for our between subjects one-way ANOVA. So that is our sum squares between divided by our sum squares between plus sum squares within. So that is our sum squares between divided by our sum squares total. So your partial eta squared, in the case of a true experiment, tells you the percentage of the variation in your DV that is caused by your treatment. Now, if you don't have a true experiment, you have a quasi-experiment, you would still know it's the percentage of total variation in your DV that is associated with your independent variable or your manipulation. When you're looking at it within subjects ANOVA, it's a little different, but the interpretation is exactly the same. It's sum squares between divided by sum squares between plus sum squares error. It's still the percentage of total variation that is unaccounted for, that is driven by our independent variable. So the only difference between the within and between is that in the within, we've removed the sum squares subjects from our within estimate. That is not error. That is accounted for variance, so we remove it out. So of the variance that's unaccounted for, what percentage of that is caused by our manipulation or is associated with our quasi-experimental manipulation? Step 5, make your graph. This one's easy. The graph maker is super simple.
So in step number 6, this is our last step. We're going to create an ANOVA table, or fill one out more realistically. We're going to just state at the beginning, before we did any statistics, which groups had the highest to lowest means. So this is not mathematical difference. This is just knowing the direction of our difference. We are going to interpret our p-value. Was the difference statistically different? Did we disprove the null? Do we know nothing? We're going to interpret our effect size and our 90% confidence interval of the effect size. In this case, it's partial eta squared. And we use the 90%, not the 95%, because research has shown that the 95% is just a little bit too spread out to be useful.
This is an ANOVA table. All it is it tells you all your different sources of variation. So you're between, you're within, your subjects, and your error. You have to put in your sum squares for each of those components in those columns. You just put an equal sign and an enter, and then you enter in the numbers. Degrees of freedom, the same thing. Your degrees of freedom between, within, subjects, and degrees of freedom error. Then you calculate your variance, all the variances you can calculate, which is all 4 of these variances. Then you calculate your F ratio, which is only your variance of your signal divided by your variance of your noise. That gives you your F ratio. SPSS gives you your p-value. Your partial eta squared, I'll show you how to get that. Your 90% confidence interval of your partial eta squared, you put that on here as well. ANOVA will tell us if there's a difference among the 3 means, but it doesn't tell us where the difference exists. You must run follow-up tests. The first follow-up test is called Fisher's LSD, but really, it's just you do all the t-tests that are possible, like you normally would. So, the pros. This is super easy. You already know how to do this. This is the best option for within subjects designs. It has the most power, and Fisher's LSD is standard operating practice in neuroscience. They don't really do anything except for follow-up t-tests. They don't do the corrections that we're going to talk about in a second. So your first option is Fisher's LSD, and this is the option that you should use for all within subjects one-way ANOVAs. Now, the cons of this I'm going to talk about in a second, but I want to state one more time, this is the choice for within subjects design. Bonferroni said, I don't really think what Fisher is doing is correct. What he suggests is that we multiply our p-values that we find in our t-tests by the number of tests that we ran. This will make it harder to find significance. So we're like, what is this bozo doing to us? He's making it harder to find significance. I'm going to explain why in a second. The pros, Bonferroni is super easy to do. You just run regular old t-tests, and then you multiply your p-value by the number of t-tests you ran. If you ran 5 follow-up t-tests, you multiply your p-value by 5. The cons of this test, it's way too conservative. I will hit on that in a moment, but essentially what's going to happen is you're going to find omnibus ANOVAs all over the place. You're going to find that your ANOVA was significant. However, your you're not going to find where that difference, what's causing that difference. Because when you use a Bonferroni, it's too conservative. You're really hurting yourself in terms of finding what's driving that difference. So a lot of folks don't recommend Bonferroni, but it's super easy to use. But where did Bonferroni come up with this idea? I'll explain that in the next slide. So Bonferroni was just sitting there and thinking like, okay, so for the most part, scientific fields have set their level of rejection at 0.05. Anytime you have a p less than 0.05, you reject the null hypothesis. However, there is a probability that you would reject the null hypothesis and the null hypothesis were true. This is like a fact. This is a fact of statistics. So if you look at this on any given test, that we run as psychologists, there's a 5% chance or a probability of 0.05 that we would reject a null when it's actually true. On any given test, we have a 5% chance of having this happen. And any test we run. So that means out of 100 tests, 5 will be false positives. Out of 20 tests that we run, 1 will be a false positive. And Bonferroni's sort of sitting there like, wait. This p-value of 0.05 is set to be a p-value of 0.05 because we as scientists, pretty much all scientists, with the exception of physicists who are better at math than the rest of us, but pretty much have stated that we are not willing to take a risk greater than 5% of a false positive. That is falsely rejecting a non-significant null, right? So we're only willing to take 5% of a risk. So that's okay on any individual test that we run. We have a 5% risk of doing this. So on our Anova, we have a 5% risk. On any t-test that we've run so far, we have a 5% risk. But now we're in the follow-up range. And Bonferroni's sitting there and saying, okay, if we do 3 follow-ups, what's the probability that we would falsely make a false positive, falsely reject a null that's true, right? Say a result is significant when in the real world, the populations are the same. So he's like, wait. We've run 3 tests here. Each of those tests have a probability of a false positive of 5%. So if we run 3, the probability of a false positive is actually 15%, and we have to adjust our p-value accordingly. So Bonferroni's probably this is the simplest test. This is, from my understanding, it's been around forever. It probably wasn't a test that people paid that much attention to when it first came out in a long way back times ago. But essentially, it's just saying, hey. So if we run a t-test and we find a significant result in a set of 3, we have to multiply all our p-values by 3 to find the true p-value. That's essentially how it works. That's really all you have to do. Bonferroni's super easy. For me, it's just super easy to do. You just take your p-value, multiply it by the number of tests that you ran. For all the examples we've been using, it's been 3. But it's still a basic idea and it has a point. Like when you run multiple t-tests, when you do that, your probability of finding at least one false positive is not 0.05%. It's 0.05 it's not 5%. It's 5% times the number of tests you ran. So this is why you multiply your p-value by the number of tests you ran. If you're confused, remember, a large p-value is bad. So you're making your p-values larger. That's why you multiply it by 3. Very simple idea.
So Tukey noticed the same problem that Bonferroni did. He said, wait, our probability of a false positive is much higher than we think it is, and we set our p-value to 0.05 because we don't want false positives greater than 5%, but we actually have a much greater false positive sense. He also was like, that Bonferroni correction, that thing is too extreme. And so he sat down, real statistician, and figured some stuff out. He didn't use the common sense approach like Bonferroni's using. He used a mathematical based approach that he tested and examined with various equations. And he ended up with what we know is Tukey's honestly significant difference. So what is Tukey's HSD? It's a t-test with a different formula for the bottom, right? For the standard error. So the first part of the t-test is still the same. Signal, mean difference, right? Mean difference over. Then we got this funky equation on the bottom. The square root of mean squared error divided by NH. Now we have to think about this as the square root of mean squared error divided by the square root of NH. And now let's tackle the square root of mean squared error. Now mean squared is just another word for variance. So the square root of your error variance that you use in your ANOVA. So wait. Variance is standard deviation squared. So the square root of variance, oh, that's the standard deviation of our error term. That's what's going on there. So on the top, we take whatever our error term is. In a between subjects design, it's that within component. In a within subjects design, it's that error component. But we just throw that in there. The computers do it for us, but I want you to know what's going on. But we throw in our standard deviation of our error component for our test. And we divide that by the square root of this funky n. Now, this funky n is called the harmonic mean of n. And so essentially what you got to do is you got to average your two sample sizes together in any t-test. So unless they're equal. So how are we going to do that? We're going to use the harmonic mean, which is old. I believe it was created by Pythagoras, the Pythagorean theorem. Like, same guy. That's how long this has been around. And it's still a mean, but you're going to have a hard time, just like I do, believing that it works. So what is the formula for a harmonic mean? All it is the mean formula flipped and flipped. So the top of this formula is the number of numbers being averaged together. In our example, it's always 2, so I'm going to keep 2 here for this specific test. So it's like, okay, on top, we put the number of numbers being averaged together, which is the exact opposite of what we normally do, divided by the reciprocal of the ends or the numbers we're trying to average. So 1 over the number being averaged plus 1 over the number being averaged. So, like, how does this work? Let me just show you how the math works. So, when we have equal n, it works identically to how the normal average works. Don't ask me why. I don't know why. It seems weird that it does work, but it does. So, we can see it in action. We're averaging 2 numbers together, so 2 goes on the top, divided by the reciprocal of the 2 numbers we're averaging. Let's say those 2 numbers are 4. Both groups had a sample size of 4. So 2 divided by 1 over 4 plus 1 over 4. Let's break that down one more time. 2 divided by 1 over 4 is 2 divided by 0.25 plus 0.25. So 2 divided by 0.25 plus 0.25 equals 0.50. 2 divided by a half is equal to 4. And that's because a half fits into 1 twice, and so it fits into 2 4 times. If you don't believe me, that's all division is. Now, that's the same mean we would expect. Where the harmonic mean is really helpful is, it's not too happy when numbers are different. So it has a drastically different response when the 2 numbers being averaged are different. Let's see that again. We're going to assume our 2 means the n of 1 is 1 and the n of the other one is 4. So we do the same formula. 2 over 1 over 1 plus 1 over 4. So that's 2 over 1 plus 0.25. 2 over 1.25 equals 1.6. Our normal mean would have been a 2.5. So the harmonic mean really is disadvantaging unequal sample sizes, because unequal sample sizes lead to all sorts of weird examinations of numbers. Particularly, I would argue that's kind of true for the bowling examples that we've had in the past. But ultimately, this is how it works. Tukey's HSD, you're not going to be able to see why it works, but it's more conservative than LSD, just running all the t-tests, and it's way less conservative than Bonferroni's simple non-mathematical solution. So Tukey's HSD is what you should use for between subjects design. And you're like, wait, why don't we use it for within subjects design? Because it just provides too conservative of a response. We've looked at the data from a statistician kind of lens, and what we find is that if we try to apply this to our within subjects data, it doesn't lead to the most accurate responses. So for the within subjects data, we should just do the normal t-tests. But for the between subjects data, we should use Tukey's. And now to kind of make sense when I'm doing all of the data analysis, that you can't really find Tukey's for within subjects design because statisticians have agreed it's a bad call. That's the answer right there. Now, also, I'm going to be honest about it. People are moving away from these post hoc tests. And so in general, like we're moving away from these post hoc tests and ANOVA to some degree. And I'll get you caught up on that by the end of the semester. But people are moving away from this. So it's also like one of those things where you can't find stats programs that calculate it. And if I wanted to calculate it, I'd have to run the ANOVA. I'd have to take my variance error or my standard deviation error, put it on the top down there. I'd have to calculate my own harmonic mean, and then I have to run the t-test with various degrees of freedom. So, but yeah. So I want to tell you something really unfortunate. Each of our follow-up tests has its own 6 steps. That means every t-test that we conduct after the Omnibus ANOVA, if we conduct 3, we're going to have 3 separate 6 steps. Now, I'm going to really shorten those up. You'll see me go through a problem in a second. I'm really going to shorten up those steps. But I want you to know that each of these t-tests has a null. Each of these t-tests has a Cohen's d. Each of these t-tests has all the stuff that all the t-tests have had forever. So I'm sorry to break this to you, but that's what it is. And right now we're going to start solving a problem together. All right, so we are going to analyze the data I've been looking at for the last week or so. First as a between subjects ANOVA, and then second as a within subjects ANOVA. So here's the problem I'm going to work on with you. All right, finding outliers is pretty simple. So we have 3 or more group means. What we have to do is we have to take all the scores that make each of those group means. We have to take those scores, throw them in our MAD outlier and MAD outlier detector and see if we have any outliers. Now, if we do, and it's a between subjects design, we just remove that outlier. But if we have an outlier and it's a within subjects design, we have to remove that person's scores from every single condition. That's just how it works. There's no other way around it. Otherwise, you can't get the advantages of the within subjects ANOVA. So essentially, I just plug my numbers in, check for the outlier, just like before. But I'm going to have to do it 3 times, once for each of the conditions. Now, I'm not going to do it because you can easily see me doing it. I'm not trying to waste your time. I will tell you I had 1 outlier in condition number 3, but I didn't remove them because I wanted the numbers to be consistent with the previous lectures. So I should have removed it, but I didn't.
left, we have it entered correctly for a within subjects one-way ANOVA. On the right, we have it entered correctly for a between subjects one-way ANOVA. Now, essentially, in SPSS, it's one row per participant. So this is all of Mighty scores. This is all of Mickey scores. This is all of Mini scores. This is all of Modest scores. So that's technically how you would enter this in. So when it's within subjects, you have a column for dependent variables in the control group. You have a column for dependent variable in the 10-gram condition and a column of the dependent variable for those in the 100-gram condition. Now let's imagine we had 12 different mice. I'd put in I could put in a participant column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are different mice in 3 different conditions. 4 of these mice were in the control, 4 were in the 10 gram, and 4 were in the 100 gram. And the dependent variable is sleeping. So for a between subjects one-way ANOVA, all you need is 2 columns. For within subjects, you need 1 column per each condition. So now let's move on to our first analysis. How do we analyze this data as if it were a between subjects ANOVA? Okay, so that is, we're assuming different mice in different conditions. We're going to use this data set right here. So we go analyze, compare means, one-way ANOVA. I'm going to click that again, analyze, compare means, one-way ANOVA. Analyze, compare means, one-way ANOVA. Analyze, compare means, one-way ANOVA. Just want to make sure you're in the same place. And then there's all these different names for dependent variable and independent variable, and you just got to look for them. Factor is a name for independent variable. Dependent is clearly our dependent variable. I have 5 columns here, but remember, we're only focusing on these 2 because we're doing the between subjects ANOVA. So our dependent list is my dependent variable, and my between factor is my between subjects variable. And that's pretty great. I want to click on postdocs, and I want to go ahead and click on both of these postdocs because these are the ones that you're going to use. Okay. Tukey's, Bonferroni, or LSD. Now, LSD is literally just do all t-tests. That's it. No correction. Bonferroni is that very extreme correction. And Tukey's is a less extreme correction. So we're going to go ahead and click continue on that. I'm going to look in options. I want descriptives. I want a means plot. So make sure descriptives is clicked. Make sure a means plot is clicked. And this is just missing variables. What do you do with that? Well, I mean, don't even worry about that. Okay, so I'm going to go through this again. I didn't click anything for contrast. Postdocs, you only have to click 1, but I'm going to click all 3. LSD is just do all the t-tests. Bonferroni is correct with that very conservative issue, and Tukey's is correct with that least conservative issue. So I click OK. Here, I clicked on my options, descriptives, and means plot. That was it. Postdocs, I clicked on my postdoc options. You only need to click 1. I'm clicking on all 3 for illustration. Nothing in bootstraps. Options, you just click descriptives and means plot. So postdoc, I clicked all 3. You just click 1. If you can, run a Tukey's. Analyze, compare means, one-way ANOVA. I messed that up. You can see it didn't do anything because I'm in it. So that'll get you here. You click in your DV. You click in your IV. DV on the top, dependent. IV on the bottom, factor. Postdocs, options, descriptives, and means plot. I click OK. And what you see here is a very beautiful output. So first things first, my descriptives, my means, my standard deviations for groups 1, 2, and 3. Maybe I should have used those labels to tell me that this was the control, that this was the 10 gram, this was the 100 gram, but I didn't. So we're just going to have to deal with that, right? So this is one of those downsides of being disorganized. When you're more organized and you take that moment to insert in those labels, it'll tell you 1, 2, and 3 are here. But I'm still not going to do it. It doesn't matter. That's just like, you got to know what you're doing. You got to be like me and be like, I'm going to go back and check that group 1 is my control, group 2 is my 10 gram, and group 3 is my 100 gram. But no big deal. Means and standard deviations, you're going to need those. ANOVA, you see The source table, your between groups source, your independent variable, your sums of squares is 255.5. Your within groups, that's your within each condition. Your sums of squares is 174.75. Your total is 430.25. This is what we found earlier. Your mean squared is just variance. So this is 255 divided by 2. This is 174 divided by 9. So we get 127 divided by 19. There's decimal places. I'm not going to mention them. Our F ratio is 6.579, and our p-value is 0.017. So that's the ANOVA. Now what we have underneath it are our follow-up tests, and we have a whole bunch because I did them 3 different ways. And let's just look at them first, just as if they were just normal t-tests, right? Just normal t-tests right here. So I'm going to look at the LSD. I wish I would have ordered it differently, but I got 1 versus 2, right? My p-value is 0.3. Okay. So 0.324. 1 versus 3, just in a normal t-test, p-value is 0.006. And then we got 2 versus 3, my p-value is 0.035. So when I run the 3 tests, I get 2 significant differences and 1 non-significant difference. So I get group 1 versus group 2 is not significant, but 1 versus 3 is significant and 2 versus 3 is significant. So those are the results we get when we just do the LSD, which is just, I mean, I guess now you're like, shit, it doesn't report my t-test. But what you should know is that a t-test is nothing more than your mean difference divided by your standard error. So you can calculate those. Also, 1 versus 2 and 2 versus 1, you get a negative, you get a positive, you get the same p-value. 1 versus 2, 2 versus 1, negative, positive, same p-value, same test, same confidence interval, same everything, okay? LSD is just running all the follow-up t-tests that you can do. Bonferroni is what I said earlier, is you just take your p-value from normal t-tests and multiply it by the number of tests you ran. Well, we only ran 3 tests here. 1 versus 2, 1 versus 3, 2 versus 3, because 2 versus 1, we already did that. 3 versus 1, we already did that. 3 versus 2, we already did that. So there's only 3 unique tests happening here. Bonferroni is just taking your p-value and multiplying it by the number of tests. So let's see if that works out. Is 0.324 times 3 0.9 something? Yes, it is. Is 0.066 times 3 0.018? Yes, it is. There's probably some numbers we're not seeing, so it's close enough, right? There's definitely numbers we're not seeing. And then is, let me see here, 0.035 times 3 0.10 something. Yes, it is. And you can see that the difference between the LSD and the Bonferroni is nothing special. All it is, Bonferroni is super easy, just saying, hey, you ran 3 tests, multiply your p-value by 3. Super simple. Your Tukey's HSD is going to have p-values that are in between your LSD and your Bonferroni. So that's really what's going on here, right? So you run Tukey's HSD, which I talked about, and you can see that we will still have the group 1 versus 3 being a significant difference, but no other difference is significant. All right, so we got that 0.016 here for that comparison is 0.006. Those are different, but it's not super easy for you to see where that difference comes from unless you know what's going on. Nonetheless, you can see that LSD is the least conservative test, Bonferroni is the most conservative, and Tukey's is in the middle in terms of conservativeness. Now, I don't mean voting for Republicans or Democrats. I mean conservative in that it's less likely to find a significant difference. So LSD is the most likely, Bonferroni is the least likely, Tukey's HSD is in the middle. But that's our proof right there for these different tests. Now let's see what changes when we analyze this appropriately, like within subject's design, and we get rid of that sum squares subjects term from our error term. So we got this time analyze general linear model repeated measures. Analyze general linear model repeated measures. Analyze GLM repeated measures. Analyze GLM repeated measures. Analyze GLM repeated measures. You should be with me by now. Then I've done this before because I always practice. Don't judge me. But now I'm like, okay, I got a drug dose condition with 3 levels. I'm going to add that to this model here. I'm going to click add. So I'm going to show you that again. I'm going to remove drug dose, 3 levels, add. Drug dose, 3 levels, add. Drug dose, 3 levels, add. Yes, right, you can see. That's how it works. Click define. That's just a weird error. Don't worry about that. So now we get this thing pops up. And it's like, okay, I got to put in my scores for control, my scores for 10 gram, and my scores for 100 gram into those 3 boxes. I do that. And don't worry about model or contrast. I do want you to click on plots, and I want you to click your drug dose into that horizontal axis plot. What you don't know is that that's the only plot that will work. That's the only plot you can do when you have 1 independent variable. If you have 2, you choose which variable goes in the horizontal axis and which variable goes in separate lines. If you had 3 independent variables, you make separate plots. You don't have to worry. If that doesn't make sense, don't worry about it. I want a plot for drug dose. We only have 1 independent variable, so it's drug dose on sleeping. I make sure to click it in. I click add. I make sure to click it in. I click add. It's not adding it because it's already there. I make sure to click it in. I click add. Click continue. No big deal. I click on my post hocs and nothing's there, and that is so annoying. They're the same post hocs, same tests for the between subjects stuff. So you're like, I'm screwed. I'm gonna have to do these all by hand. There's nothing in the save that I want you to look at. But here, I want you to take your drug dose, throw it into the display means for drug dose. This right here says compare main effects. That's going to allow you to get those follow-up tests. And here it doesn't let me choose more than one. I've tried. It doesn't let me. Okay. So LSD is just your traditional test that it's going to do, that all the t-tests, which is what I suggest you all should do. I want to click my descriptive statistics here. And you're going to see that the within subjects ANOVA generally sucks compared to the between subjects ANOVA in terms of how it's printed out. So I'm just warning you for that. Let's just go over what I did. Step number 1, click in my means. That's it. Click my plots, click in just horizontal and add. Okay, my one factor is in there, and then I click on my options. I made sure to click drug dose into my display means. Compare main effects for LSD, and I also clicked on descriptive statistics. I click OK, and I told you the output was going to be horrible. Okay, and it is. It's just nasty. So first thing, you get a list of factors. So it's like when 1 is mentioned below, it's going to be the control group. 2 and 3, so forth. 10 gram, 100 gram. Our descriptive statistics are just means and standard deviations. That is great. That is awesome. I'm very happy with that. That makes life so much easier. You have to report those, so that's great. And when we look at this, we see that the 100 gram group slept a lot more than the other 2 groups. That's what I'm seeing right now. This multivariate test, you want to delete it. So if you're on a PC, you literally click the delete button. If you're on a Mac, you got to click function delete. It gets rid of it. We also didn't talk about that, so bye-bye. Now we got our test of within subjects effects. And when I was telling you that the output was horrendous, it is. So basically, it has 3 things you can ignore. These bottom 3 rows we're not going to talk about. You're going to ignore. You can learn about them later, but just ignore them. Do not pay attention to those at all. So now we got our drug dose with a sum squares of 255. Well, let's go back up to our between subjects analysis. Oh, drug dose. That's our between groups term. Awesome. You can see that they match perfectly. That's the same term. And then you got an error term. That doesn't match with anything up there at all. Our error term is that just like the actual error term. Remember, it was sum squares within minus sum squares subjects equals sum squares error. Well, that's what we have here. And then we also have this test of within subjects contrast, delete, and then we got this test of between subjects effects. That's the effect of your subjects, the effect of your participants. So essentially, what we have here in this ANOVA is our between term, our error term, our subjects term. We don't have the total term, right? But we can easily calculate that by just adding all the error plus the drug dose. So that's like the subject's error, the unknown error, and the drug dose. And that'll get us total that we have. But that's degrees of freedom. It's still 2 plus 6 plus 3. So that's 11, right? You're also not given your within subject's term, which is literally for that. So remember, your within subject's term is with the participant still in it. So it's this plus this. That's your sum squares. This 49.83 plus your 124.917. That's your sum squares within. Your degrees of freedom within are 6 plus 3. That's 9. You'll see that all the math works out. But when you're doing the within subjects effects, you're not going to get the total and you're not going to get the within. It's not going to tell you those two. So yeah, I'm just letting you know that's how it works. But essentially, when we're looking at this, we got the main thing we're interested in is our F value, right? There's no F value associated with our subjects effect. That's actually removed from our analysis. But there's error that we don't know where it's coming from. What you'll notice here, when you compare the within subjects analysis to the between subjects analysis, is that the F ratio is much larger. Here, I'll go up and show you. Our F ratio is almost double the size. But that is because we were able to remove all this error variation from the within subjects estimate to make a smaller error term.
All right, there's one more thing you need to do, and I just realized you needed it for the post hoc effect sizes. So you have to find the correlations for the within subjects ANOVA. So this one over here, the correlations between each of these observations. So analyze, correlate, bivariate, and you're just going to look at throw in all your within subjects variables. This is control, 10 gram and 100 gram. You throw those all together to see how they're correlated. You click OK, and you get your correlations down here that you're going to need to put in. Sorry for the click. You get your correlations down here that you're going to need to put in for that Cohen's d follow-up test to your the Cohen's d's for your follow-up tests. The one-way between subjects ANOVA with PSPP. So I have my data entered, one row per participant. It's between subjects, so you have one coding variable and one dependent variable. So it's great. I love that. Analyze, compare means, one-way ANOVA. All you do is you plug in your dependent variable into your dependent variable and your independent variable into your factor. And don't click OK. Click paste. Now, what you see here is computer code, and we need to do this. We need to do this in order to get our post hoc tests. So I pasted it. Now I highlight it. Now I click run. I click all, and I get all my results. And they're exactly the same as before. So here we have our descriptive statistics. We got mean, standard deviation, standard errors, other things that don't matter. We have our ANOVA output, our between, our within, and our total components, our sum squares, our degrees of freedom, our variance. We don't have it down here. Our F, which is just this divided by this. And then we have our Tukey's HSD, which is controlling for all those things we talked about earlier, and we're getting the same result that we got earlier. So we have a p-value 1 versus 2 of 0.57, 1 versus 3 of 0.06, 2 versus 3 of 0.08. Those are our Tukey's p-values from earlier. Now, remember, if you didn't watch the previous video, that's okay, but it doesn't give us the t-test by hand, but a t-test is just this divided by standard error. So we can get all of our t-tests here. And you can see, look at this standard error. It's all the same, right? That's because it's our variance error divided by the harmonic mean of the ends, which is going to be 4. But if we look at our mean squared, and then if we took the square root of that, and then we divided that by the harmonic mean of 4, just the square root of 4, divided that by 2, we would find that this mean is working out perfectly, which is beautiful. But I want you to see that. You can see what Tukey's is doing. It's setting this standard error equal for everybody, particularly taking the mean squared for our error, 19.47, taking the square root of that, and then dividing that by 2. All right, so you're going to find this link on our course website. You're going to click it, and you're going to follow through the next steps in the video that show you how to sort of deal with this interesting problem where PSPP doesn't work, and I'm going to have you use R, just a little tiny bit of R. It's going to take its time to open this project up, and you're going to see a screen just like this. So then you have to click this file right here, this one way within RMD file, and you got to click this file, and then you'll see all this stuff right here pop up. I'm going to click that button and hide that console because you don't need it. Wish I could oh yeah, there's the button again. So, all I did there was I clicked this button, essentially. It was here, and I said, I don't want to look at that. And one of the things you're going to see is that you're going to have an extra library called MBESS on there. That does not come installed on your workspace. So you've got to install any extra packages that I have installed. So MBESS is one. And let me see if there's any others. I do not see any others down here at all. Let me just make sure that's true. Yup, that's true there. Ooh, I don't think it's necessarily true down there. Let me just double check. All right. So what you're going to have to do is click on this packages button right here, and you're going to have to click on install. You're going to have to type in MBESS. Okay. I'm going to click install, and then if you bring that back up, nope. So you can see it's working now. It's like, okay, we're going to install MBESS, and it's going to take its time. It's saying it's installing the package. It's probably going to give me an error message because I just installed it. But if you look in your user packages and don't see it here, right? I clicked on this package button. I clicked on install and got that. But even if I don't click on install, I can see it's right here. And then I want to use it, so I got to make sure to click it. So I got library MBESS. You might need, I don't think you'll need anything else for this. But if you get any errors that don't make sense, just take a screenshot, send it to me so I can update this. Because this is just like me being me. This is me showing you how I do my data analyses. And you can see it's quite complicated. So if you get any weird errors that say, oh, this is not a function or anything like that,
let me know what those errors are saying, and then I can tell you what if you need to download any more programs. So, but first things first, this is the one way within subjects ANOVA. Our first thing is for our 90% CI of eta squared. Everyone's going to have to come back to this and look at this. But essentially, all you have to do, I'm going to leave that for itself. All you have to do to do the one way within subjects ANOVA is go to this second box, 90% CI of eta squared. Nope, that's my output. Don't need that. One way within subjects ANOVA. Yep. PSPP does not handle this. Yep. Enter in your data in the gray box below. Super. See what I have and modify it for your problems. Cool. Then I have some more things. You have to use words for the independent variable descriptors. You have to use words here. You can't use numbers or that messes everything up. You have to use a number for your dependent variable. That makes sense. And you have to use letters for your participants. Letters are words. You can see I chose ABC, ABC, ABC. So all you have to do is enter in your data in this area and hit this run button and everything will work. So let's just pull up our data. I want to see if I can get my data here. Window. I think that's my data. Yep. I'm going to get my data up here. I'm going to make sure I'm in studio. I'm going to enter it. So first things first, I have 4 people in the control condition. So I got to put in another comma, hit the one quote button, control, hit the one quote button again. Hit it. Now I got to hit 10 gram, add another comma. You can see what I'm doing there. Then, comma, 100 gram. The same exact way. Then I'm going to enter my data. So I got the 8, 10, and 5 in there. I do not have the 3. I have the 11, 16, 6. I don't have the other 6. I've kind of been playing around with this. 20, 19, 21. I do not have the 10. So then I got A, B, C, D. I got 4 participants in there. So I got to put in participant D, A, B, C, D, A, B, C, comma, single quote, D, single quote. And now all I should have to do, assuming all my projects are here and everything's clicked, is click this run button. I want to see if it clicked any other things. Nope, just MBESS. Everything else comes with it. And so that's all you have to do. And here you go. It spits out this beautiful output. So first things first, it says our error associated with our within subjects ID. Well, my within subjects ID was just A, B, C, and D. And this is telling me my subjects component. So this is, they're saying residuals, but you just got to get used to that. But this is I had 4 participants. Degrees of freedom is 3. So that's matching. My sum squares matches from before. My mean squared matches from before. That's my subjects component. Then we got the next part where it's like my independent variable, which is my between component, and my residuals, which is my error component. You can see these all match up as well. And my p-value is 0.0043. So then I have to do my follow-up t-tests. I have a significant omnibus ANOVA. I have to do my follow-up t-tests. And what I have here is I have descriptive statistics with means and standard deviations. So we got my 100 gram group, 10 gram group, and my control varied in sleep. And we got the same thing in terms of standard deviations right here. Same standard deviations, same groups. Then we have these are our p-values. The first thing that it reports are your p-values. So these are the p-values for your t-test. So 10 gram to 100 gram, control to 100 gram, control to 10 gram. You just got to pull those out. It gives you your t scores right here. So these are your t scores and these are your degrees of freedom. So you'd write t parentheses degrees of freedom 3 equals 2.81 or negative 2.81. It doesn't really matter if you do negative or positive on these. Comma p equals 0.067. So again, then we got T with 3 degrees of freedom equals negative 5.62 or 5.62, comma p-value 0.011, and we have the control versus the 10 gram. So that is a t-test with parentheses 3 degrees of freedom. The t equals 3.15, the p equals 0.051. So that's how you run it within subjects one-way ANOVA with R. Super easy. Installing it, getting it to work may not be super easy. If you struggle with this, please send me a text. You'll be able to text me. So that's how it works. This is my write-up. And you have your test statistic and your p-value, and your p-value decision, you have to interpret it. So what's all this mean? So first you write up your F stat this way. F with 2 and 6 degrees of freedom, top and bottom degrees of freedom, equals 15.381. I'm doing the within subjects ANOVA, one-way ANOVA, so I'm just reporting that for you. And my p-value equals 0.004. So I got my test statistic on there. I got my p-value on there. Now I have to interpret my test statistic. So my test statistic is very simple. My signal is 14.38 times the size of my noise, f minus 1. That's my signal to noise ratio. So I want that to be clear. That's beautiful and perfect. And then, this is the omnibus test. So this decision really affects how difficult your homework is. And if you retain your null hypothesis, you don't do any of the follow-ups. You don't have to do anything. You're just done. But right here, we've rejected our null hypothesis, so we have to do those follow-up tests. But when I'm asking you to report the test statistic and the p-value, I want you to treat all the follow-ups like we haven't even talked about them yet. Yes, we did the PSPP and SPSS to get them, but that's just because it's easier. But I want you just to act like they don't exist. This is just for the omnibus test. And so what we know is that our 3 means are not the same. Our p-value is less than 0.05. We reject the null. The null is that the 3 means are the same, or that our f equals 1. We know that our f does not equal 1. But we also don't know why the f does not equal 1. That means where the difference exists. That will require us to set up a whole new 6 steps and do the post hoc test, which I'll show you at the end when I finalize this problem, because I want to show you how to do those 6 steps as well. But nonetheless, this is not a very this is not a very large problem. All we have to do is, sorry, it changed from dark to light mode and it freaked me out. But all we have to do is state those very simple things. So we do have a mathematical difference. I just don't know where the difference is. I know that there's a difference among the 3 means. I don't know where it is. I have to run another set of tests. But essentially, that's it. That's it. We have my F statistic. I reported it appropriately there. I have my p-value. I reject the null. My F statistic -1 tells me signal to noise ratio. My p-value tells me reject or retain the null. In this case, I know there's an omnibus difference. There's a difference somewhere, but I don't know where the difference exists. All right, so how do we calculate our effect size for our omnibus one-way ANOVAs? Super easy. I've already showed you the link and all that stuff, and I've showed you how to log in. So now I'm going to be like, okay, you go to the top of this sheet. If you haven't seen this before, this is R. And there's instructions. In the gray box below, change your F value to your F value. Change your degrees of freedom top to your degrees of freedom numerator, between, or top. I don't care how you think about it. Change your DF bottom equal to your degrees of freedom of your denominator error term or your bottom. Click the run button right here and the code will work. So I have one of my F statistics in here. So it's 15.38. This is when I ran my data. So my F is definitely stay on the page. 15.38. My degrees of freedom top. Well, I can go down here and look. My degrees of freedom top were 2. My degrees of freedom bottom were 6. So I got 2 and 6. And then all I do, don't worry about anything below there. I just click my run button. And you can see my partial eta squared was 0.61. My independent variable accounted for 62% of the variation in the dependent variable. Actually caused, I can say caused because it was a manipulation. I'm 95% confident that in the worst case scenario, my independent variable caused 35% of the changes in the dependent variable, and my best case scenario, it caused 89% of the variation or changes in my dependent variable. How do we find our Cohen's d's for the follow-up tests? The same way we've been doing it throughout the semester. So is this a t-test? Yes, it is. Is it a comparison between correlated samples? Yes, the one I'm working on is. Do you have the mean, standard deviations, R's, and N's? Yes, I do. And in fact, I've already entered them because I'm that crafty, right? So we got our mean one of 6.5. That's our control. 10 gram mean, 9.75. Standard deviation 1 is 3.109. Standard deviation 2 is 4.79. My number of pairs are 4. My correlation is 0.95. And that's the correlation I found earlier that I talked about. So I have to plug that in. Now I get my Cohen's d of 1.5 with a 95% confidence interval from tiny but in the opposite direction to massive in a big direction. Now we got to remember that the p-value was greater than 0.05 here, so we do expect to see that 0 in the range. But essentially, what we're seeing here is that we're just doing it the same way. So then I enter in the same means and standard deviations. Remember, my second problem was just do it like a between subjects design. My groups are 4 and 4. And when I ran that, at first, it just looked weird to me. My Cohen's d was 0.8, and then my 95% confidence interval was 2.5, negative 2.5 to 0.9, and I knew something was wrong. And it wasn't that wrong. I have the same Cohen's d value. But this interval's for when it's negative. So this is kind of what I'm talking about here with Cohen's d's. Like, if you look here, and I've added this column there so you know how to adjust yourself. But you can either report your Cohen's d as negative, or if you report it as positive, this one becomes negative and that one becomes positive. I'm actually a fan of reporting it as positive, with this one as negative and this one as positive. But I would just copy and paste that into my file. All right, so our Anova graph maker is super easy. What you have to do is you have to plug in your means. You have to plug in your standard deviations. You have to plug in your ends. You have to plug in your title. You have to plug in your horizontal axis. Let me fix that. You have to plug in your dependent variable. And that's it. It makes the graph for you. This is pretty perfect. You may not like the styling of it, but you know, it does its job. Put a sheet up on our website that'll make our life easier. But essentially, let's go through all the steps. 0 outliers. There were some technically, but I didn't remove them for consistency, making a note of that. Step number 1, state your null and draw out your picture. F equals 1. That's my null hypothesis, that my F ratio equals 1. Here's my picture of my F ratio. You can see I have both degrees of freedom for the bottom in there for both my effects because I'm going to paste it twice when I do my second one. But right now I'm just working on the within subjects one, so technically that should be 6. So run all my programs. This one is my within subjects SPSS output. This is just everything I got there. Um, Additionally, I threw my output from my eta squared R calculator right in there as well. My test statistic, p-value plus p-value decision, interpret the test statistic. So F 2 and 6 degrees of freedom equals 15.381. My p equals 0.004. My signal is 14.38 times the size of my noise. And that was just -1. And this is a statistical difference. I know there's a difference somewhere between the three means. Step number 4, my effect size is 0.616. My 95% confidence interval of my effect size is 0.35 to 0.8. I can change that to be consistent. 9. Cohen's rules for eta squared are 1% equals small, 9% equals medium, 25% equals massive. So what I know here is that my independent variable accounted for 62% of the variation in my dependent variable. My 95% confidence interval of this estimate is 35% to 89%. These are all considered massively large by Cohen. Cohen's rules for interpreting eta squared, which are just correlation squared, is 1% is small, 9% is medium, 25% is massive. So this is 35% to 89%. Both are massive. So I know the effect is large to large. This omnibus ANOVA has a massive effect out there. My picture is from my super easy to get, no big deal. My short interpretation. State which groups had higher means. My 10-gram group slept more than my 100-gram group, which slept more than my 0-gram control group. Now, I don't mean that significantly. I just mean that in terms of numbers. Math, we disprove the null. We know a difference among the three means exists. We don't know where. The effect, 61% of variation in our DV is caused by our IV. This is a massive effect according to Cohen. We are 90% confident that our true partial eta squared lies somewhere between 35 and 89%. Both of these are massive effects. We are confident that we have a massive effect. What you didn't see was my ANOVA table completely filled out. Sum squares between equals 255. I pulled that out of here. My sum squares within equals 174.85. I had to calculate that. Sum square subjects, 124.92. Let me show you where I got that from. So that is literally just right there. Sum squares error, that one's easy to find. That's literally right here, 49 point whatever. To find my within, all I did was add these two together. I did the same thing here, added the degrees of freedom to get that as well. So now I have my variance calculations. This divided by this equals this. 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 I could have done total too, but I didn't. It's fine. You don't need to do it. It's not the end of the world. My F ratio is just this divided by this, right? It's this divided by this. This is not the error term. This is subjects. So, that's just what it is. My p-value is what it was. And there's my eta squared and my partial eta squared. It summarizes everything for me. So you're going to have this example to just work off of. Then, okay, we got follow-up tests. Let's cut some corners here. I'm not going to be super rigid about the follow-up tests. Be very, very specific and controlled about these tests here. And then your follow-up tests. Okay, so my null hypothesis, control versus 10 gram, has its own null. So mu1 minus mu2 equals 0. You've seen this guy before. I just slammed one of those in there. Same thing here. It's the same hypothesis. Mu1 minus mu2 equals 0. Same thing. They're all the same. I just gave the correct labels to let you know that I'm testing 3 different null hypotheses, even though they are exactly the same. Then I just throw in, I have my pairwise values right here that I got, right? So that's my SPSS. Additionally, I should probably put these up there, so I'm going to go ahead and put these up there too. These are the correlations that I'm going to need to calculate my effect sizes. And also, I have my means and standard deviations, my descriptive statistics, here as well. So these are all the outputs from SPSS that we're going to need to calculate all the different t values. And what you'll notice here is that in step 3, I got to calculate t. Well, they didn't give it to me. They just gave me the mean difference in standard error. So I had to do division on my own. So I took mean difference divided by standard error equals my t. Mean difference divided by standard error equals my t. Mean difference divided by standard error equals my t. You can see those are all just coming from these different comparisons. So now I have my 3 t values. My degrees of freedom for all tests are 3 for this specific test. I had 4 observations in each group. It's it's a basically dependent samples t-test, so it's not number of observations, it's number of different scores, -1. 4 minus 1 is 3. I'll be lenient on degrees of freedom, but help you out. I won't make you redo it if you miss a degrees of freedom. Then, once we get to the end here, I write it up. Oh, my t with 3 degrees of freedom equals 3.25. My p equals 0.051. We know nothing. My t with 3 degrees of freedom equals this. P equals 0.001. We've disproved the null. Again, another t, degrees of freedom, so forth. T value, p value, we know nothing again. So that's great. Then these are all my Cohen's d's. You can see they're all quite large. But you can see that 2 of my Cohen's d's have pretty ridiculously wide confidence intervals. This one suggests that it could be a no effect to a massive effect. This one suggests massive to massive. This one says opposite direction to massive. So my Cohen's d, all these are large effects. They differed by many standard deviations, but there are shitty estimates throughout, with the exception of the control versus the 100 group condition. You don't have to be too specific here. I need to know I know you know what Cohen's d means. I know you know 95% confidence interval. So we're just going to push through this, right? You have to do this, but that's fine. For our table, we already got it. It's this table right here. We're good. We can see all the means. So we're not going to worry about that. Then 6, I state my mean differences. I don't have to do it different times. I can just say the 10 gram is greater than the 10 gram, or the 100 grams greater than the 10 gram, which is greater than the 0 gram. That's not in terms of math. In terms of math, 0 versus 100, yes. Nothing else was mathematically different. And you can be terse here. I don't really care. The effect size, all were large, differed by over 1 standard deviation. The confidence intervals were crappy except for the 100 group. I'm not going to make you interpret those ones too hard. We've already worked on these. So if it doesn't make sense, do those interpretations. But essentially what we just did was 1 omnibus ANOVA and 3 dependent samples t-tests. So it takes a lot, right? The steps you had to repeat. Technically, I could have made you repeat them more than just one time, but you can see we got step 1 the second time being repeated a lot. I left out the 0 because we already talked about it. I got what I need to calculate everything I need to calculate. I then got to calculate my t-test by hand, which kind of sucks. I then get my degrees of freedom for all my tests is 3. It's just how it works out. Then I get Then I just write up all my t-tests and say very shortly, we know nothing. We disprove the null. We know nothing. I provide my Cohen's d at 95% confidence intervals. I just copy them over. My interpretation, these are all large effects. However, they're crappy intervals for 2 of the 3 examinations. The one that wasn't a crappy interval, the one I'm confident in, is my control versus my 100 gram group. That's a very big difference. We don't need a picture. And here, we're just quickly summarizing it up. These are the different means, how they laid out. Then we have math difference, 0 versus 100, yes. Nothing else was mathematically different. Effect sizes, all were large, differed by over 1 standard deviation. However, my confidence intervals of the effect size were crappy, except for the control versus 100 group condition. So what I want you to notice is that I'm not really going to be too strict about these interpretations at the end. They need to be correct. You need to understand Cohen's D by now, but I'm not going to really grade those as harshly as I am going to grade this stuff up here, which isn't that bad. So essentially, that's it. All right, so here's what I want you to do for homework. I want you to take this very simple data set, and I want you to calculate the omnibus ANOVA both ways, okay, using a between subject design and assuming a within subject design. Within subject design is the correct way to analyze this data, but I want you to see how to do it both ways. Now, if you do not get a significant omnibus ANOVA, you do not have to go through with the explanations of the follow-up tests. And that's important to know. And then on top of that, there's not really much else. I just want you to solve this problem as quickly as possible, and our file drawer has everything in it, so it should work. I'm going to tell you right now, one of them's significant, one of them's not. There are no outliers, but you should still check to make sure I'm not wrong. But yeah, everything here should work. But yeah, my hints are one's significant, one's not, because I felt like it was too much work to give you one significant, one not, both significant tests, so I only gave you one. And now you got to figure out how to do it.